Alright, in this tutorial I'm going to discuss a fundamental characteristics of forces that we call conservative forces. So we are going to establish some kind of analogy between gravitational field and electric field, and show some fundamental property of electric force as related to gravitational force. First, I want you to understand this very simple concept. So in gravitation, this is an incline, this is high point, this is low point. I can also use a plus and minus, and it means the same thing. So plus for high, let's look at this as a tilt, and minus for low. Here, for example, if this is a capacitor, then this is plus, this is minus. Or I can say high and low. What is high and low? We'll say as very soon voltage, but for now just high and low. And we know the electric field will be down the hill, exactly like gravitational field down the hill. Okay, same picture. Now let's evaluate the change of gravitational potential energy versus the work done by the gravitational force on a particle going up and down. And I want you to notice this fundamental characteristic. So here, this picture, the particle is going up, and therefore the displacement dr is up. By nature, mg is always towards the ground, so the angle here is 180. Now, if I want to evaluate the work done by mg when going from this point to this point, so initial and final, then the work is just the integral from initial to final, and f which is mg dr. Now I'm not going to evaluate this work, but you understand the angle is 180, so this work is just minus mg, and the integral of the I just r, which is h in our case. This is equal. And so the work done by the gravitational force when the particle is going upward is negative. Alright, now let's evaluate the change in gravitational potential energy going from the lowest point to the highest point. By convention, the gravitational potential is put to 0 at the lowest point of the system, so this is 0. So the change in gravitational potential energy U, like this, G, I can put the gravitation, is U final minus U initial. While U final is mgh, which is equal to mgh, and initial is 0. And so this is positive, which is equal to mgh, which is positive. So now notice the relationship between these two. The work is negative, the change in potential energy is positive. They're against each other. Now let's check this case when going down. So I'm going to call this 1, and this is station 2. So now the part is going downward, and see the relationship between the work done by the gravitational force going downward and the change in potential energy in that particle. So when going down, it's hard to write with the mouse. So I'm going to evaluate the work. What is the work? Well, the work is the same. It's the integral from initial, which is high, to final, which is low, F dr. And notice now in the second picture that the vector dr and f are parallel, theta equals 0. So the integral of dr is just r, and the force is mgh, so it is just mgh. That's the work, and clearly it's positive. And it's obvious the displacement and the force are in the same direction. The work is positive. What about the change in potential energy? So, of course, gravitation, because very soon we are going to have electric. So this is U final, which is the ground, 0, minus initial, which is mgh. So this is exactly 0 minus initial is mgh. So notice this is negative. So again, what is the point here? Let's use this color. So when the work is positive, the change in potential energy is negative. And the previous case, the opposite. And so to compensate for this relationship, when one is positive, the other is negative, we can write something like this. This is probably the most important thing, and that is the change in potential energy is equal to negative work. Now, the negative work of what? The conservative work. So any force that has this characteristic, where the change in potential is equal to negative work, is called conservative force. And we are going to send the meaning of this in vector. Conservative. Conservative. Okay. All right. So this is the characteristic of this gravitational force. It is conservative force, and because the change in potential energy is equal to the negative of the work of this force on a particle within that field. Now let's see if this is true for electric force. If that is true, then we are going to call the electric force also a conservative force, and then we are going to discuss the consequence of this characteristic in lecture. Now let's apply the same idea to this capacitor. So first I'm going to go from high to low. I'm assuming this is positive particle charge. I'm going this way. This way. So what is the change in electric potential energy? Although we did not define what it is, but it's very easy. Since I'm going from high to low, the change is low, that's the final, minus high. Well, if you subtract low from high, clearly it's negative. Regardless what it is, we did not define what is electric potential energy, but that's what it is. This is final, initial, if I'm going from here to here, and this is final. So I'm going from high to low, the change is final minus initial, it is low minus high is negative. What about the work? The work of the electric force will be the same, integral from initial to final. That means from high to low. The force now is electric, not gravitational, electric, and then dl, let's call it dl. Now, notice the field is this way, and also this is dr. So they are same direction. That means the angle is 0, and cosine 0 is 1. So this is exactly, I can write Q E, that is the force, times L, which is positive. So again, now we have to highlight this. So when the work of the electric force is positive, the change in electric potential energy is negative. Now we can do it the other way. So this is from high to low. So from high to low. potential. Now what if you do it the other way? Low to high. So obviously the change in potential, electric potential energy, delta U, would be, so since I'm going from low to high, from here to here, the final is low, high, so that is high minus low. This is like 5 minus 4, which actually is positive. Now what about the work? Well, if I move in the other direction, here for example, this is the R, I'm trying to bring the particle to the left side, then the angle is 180. That means the work in that case is negative. So minus Q, I don't have to do the integral, QEL. It is the same expression like this one here. So clearly it is negative. Again, we have the same idea. So when the work is positive, negative, the change in potential energy is positive. So to compensate for this relationship, we are going to do the same thing. The change in electric potential energy is equal to the negative of the work of electric force. And so since we have demonstrated that the electric force behaves exactly like gravitational force, then it is conservative, and this work is conservative work also, like this one. Now, there are other characteristics of these forces. Let's enumerate a few of them. Here, some other characteristics of conservative forces. Here, conservative forces. So we just learn if a force is conservative, then the change in potential energy is equal to minus the conservative work. C for conservative, let's remove. Just work has to be conservative, of course. Number 2, these forces are path independent. Path independent. Independent. So what does this mean? So if this is the starting point A and this is the end point B of any given process, this is really theory. So I can do this. I can go from A to B through this path. I can also choose another path, this one, or maybe another path, let's say this one. So it doesn't matter how you go from A to B. What is relevant is the initial point and final point. I call this alpha, I call this beta, I call this gamma. And so the work of a force, if it is conservative, then that force, dr, displacement dr, through alpha, let's put alpha path, must be equal to the work beta path f dr, and it is similar to the path on gamma path, let's say f dr. That's the definition of work. We'll talk in the lecture what's the concept of work energy. They are similar. Now if this is true, because they are path independent, then the last characteristic is this. What is the work of conservative force on closed path? That means this is A and this is B. And I go this way, that is path alpha, and I come back